Greetings. So, we are discussing the electromagnetic field, and the question we stopped at in the previous class was this, that we know how to transform 4 components of a vector from one 4-dimensional flat space, space-time continuum flat space of the special theory of relativity, and that law of transformation, if the second frame which is a barred frame is moving at a constant velocity along the x axis, you can take it about any arbitrary direction, but then only some extra components are added, no new physics is added. So, I take the simple case of a frame of reference which is moving along the x axis at a constant velocity. And we are worried about how we will make this scheme work for a polar vector and an axial vector, which are both required to describe the electromagnetic field. And we talk about the electromagnetic field as something that is unified. Okay? Maxwell unified electricity and magnetism. And how did we see the unification? We saw that the vector function of one is equal to the vector function of another. Del cross E is equal to minus del B by del T. That electric fields can be produced by changing magnetic flux, the Faraday-Lenz law. And likewise, the magnetic fields can be produced by changing electric fields, which was Maxwell's, extension of this particular situation using symmetry, right? And this physics is contained in the law of transformation, which is in this 4 by 4 matrix. So, this is like an operator which operates on an operand, and then it tells you what is the new components, right. So, this is the essential term which we are looking at, and this is represented over here by this 4 by 4 matrix, right. It tells you how the components of a 4 vector transform from frame S to S bar, and all that information is contained in there. So, the electromagnetic potentials, these came as solutions of the Poinsot equation, if you remember, right. Let me just very quickly remind you about this discussion, that we discussed the uniqueness and the Helmholtz theorem, and then from the 2 equations for the curl of E and B, and from the 2 equations for the divergence of E and B, and from the boundary conditions, we can know the fields uniquely, right. We can get information about those vectors. And then if you know the curl and the vector, curl and the divergence, then you can represent them as sums of addition of an irrotational vector and a solenoidal vector. Now, when we did this, we got into the potentials, all right. But the potentials were not unique. You could have a variety of potentials which all led you to the same fields. Okay. So, these were the gauge transformations, and the potentials came, as we saw, from the solutions of the Poinsot equation. So, I am discussing the solutions using the Coulomb gauge, if you like, or you could discuss it even from the Lorentz gauge if you wish, and we considered these gauge transformations. We discussed the choices of gauges in our previous classes on electrodynamics, and you have a vector potential A and a scalar potential phi. So, you have how many scalars? 3 components of A and phi, which is 4 components, and you represent this as in terms of these 4 components A mu, as with mu going from 0, 1, 2 and 3. So, this is the representation of the electromagnetic potential, which offers itself as a natural candidate for analysis in this space-time continuum, right. And the electromagnetic fields, the fields are derivable from the potentials, right. This is what we have learnt earlier also, that the negative gradient of the potential is the electric field, and then you also have a time dependent factor whenever the fields change with time, right. So, you see that if you operate on these potentials by the derivative operators. So, you take the partial derivatives with respect to x, where x is one of the 4 dimensions including time. So, you have the 4 dimensions which are ct, x and y and z, right, which are represented as x0, x1, x2 and x3, and you can take the derivatives of the potentials and then find the corresponding fields. So, from this can you quickly see that you get E and B from these relations, right. So, you get E and B from these relations, and the electromagnetic field is represented by this F mu nu, which is called as the Maxwell electromagnetic field tensor. Mu can take 4 values, nu can take 4 values, there are 16 components in this 4 dimensional space. Okay. So, the dimensionality of the space is which is n, which is 4. Okay. The rank of the tensor is 2. So, 4 to the power 2 is 16, and these are the 16 components. Okay. But if you look at this, how the components are defined, they are defined by a difference, del A nu by del x mu minus del A mu by del x nu, and this difference can change its sign if you swap. So, it is an antisymmetric tensor. Okay. So, all the 16 components are not independent because it is an there is a built in antisymmetry, and you can also see that when mu is equal to nu, all the components go to 0, components of the field tensor go to 0. So, this is the electromagnetic field tensor of rank 2, right. So, you have got 16 components which represent the electromagnetic field, and this is an antisymmetric tensor whose diagonal elements are 0 and off diagonal elements have the opposite signs. So, that is the property of the electromagnetic field tensor. What about the charge and the current density? This will also have to be represented by 4 components, and happily the charge density together with the current density, and they are the same creatures, because what is charge at rest is current in a moving frame, right. So, it is appropriate that charge and current density come together. So, the charge density, so J0 is rho times C, so they all have this appropriate dimensions, and J is rho V as we had defined earlier, the current density vector, and the current density vector is now a 4 component, it has 4 components J0, J1, J2, J3 given by this relation. Okay. And you can see that if you take the derivatives del rho by del t plus del dot j, what do you get? You get essentially, you recover the equation of continuity. So, the equation of continuity is right there in this relation. Okay. It comes automatically, and you see how beautifully this scheme of writing vectors as 4 components, writing the current density vector as a 4 components with charge density times the speed of light and the current density together recover for you the equation of continuity, which is a well understood phenomenon earlier, right. So, the equation of continuity nicely pops out of this. So, the electromagnetic potential is now, it has got 4 components 0, 1, 2, 3. The fields are given by the derivatives of the potentials, and not just the derivatives, but difference in the derivatives between 2 terms. So, there are these del A nu by del x mu minus del A mu by del x nu. Okay. So, if you now construct the electromagnetic field tensor, and you should sit down and work this out yourself and get the derivative of A nu with respect to x mu. So, what is A nu for nu equal to 0? It is phi over c. Do you see that? It is right here on the screen. Okay. The component for mu equal to 0 is phi over c. And if you do it term by term, let nu take the 4 values 0, 1, 2, 3. So, can you see that for f0, 1 you get Ex over c? Done? Do you get Ey over c now for f0, 2? Just take the partial derivatives, take the difference. Got it? Now, this way you can get all the 16 elements, and it is easy to see that the diagonal elements are 0 and the off diagonal elements are antisymmetric. So, you can now write this field tensor with all of these derivatives taken, and the field tensor is now given by what you have on the lower left part of this screen. So, this is the electromagnetic field tensor, or the Maxwell field tensor as it is sometimes called. So, the first row has got Ex over c, Ey over c, Ez over c. Then you have minus Ex over c because it is antisymmetric. The diagonal element, the 2, 2, second row, second column is 0, and then in the off diagonal you have Bz and minus By. Okay? And that is how you generate the electromagnetic field tensor. Now, let us look at these two equations, and you will see very quickly that these equations come from a single equation if you take the derivative of the field tensor with respect to the coordinates. Okay? And this relation del f by del x nu equal to mu 0 j mu, alright, is an equation. This is not just one equation, because if you look at the Einstein summation index, nu is a dummy index. So, you have to sum over nu. Okay? So, which means that you have to take this left hand side for nu equal to 0, then add to it the same for nu equal to 1, then for nu equal to 2 and for nu equal to 3. So, when you add all the 4 pieces, you get the left hand side for the particular value of mu that you have chosen. And how many values of mu can you choose? You can choose mu equal to 0, you can choose mu equal to 1, you can choose mu equal to 2 and mu equal to 3, right. So, how many equations are you seeing over here? There are 4 equations, one for the 4 different values of mu. Nu is a dummy index which gets summed over. So, what I have written here as one equation is actually a family of 4 equations, because mu can take 4 values, nu can also take 4 values, but they all get summed over. So, it is only a dummy index. So, there are 4 equations, exactly 4 equations that I have written. Okay? And these 4 equations will turn out to be, one of these is del dot E equal to rho over epsilon 0, and the other 3 are the equations for the 3 components of the curl of B. Okay? So, del cross B equal to the right hand side is a set of 3 equations for the 3 components of the curl of B, right. For the curl of B you have got 3 components, and those 3 equations together with one equation which is the equation for divergence of E will give you 4 equations, and those are the 4 equations which are sitting here. and you can verify that very easily. So, let us write the electromagnetic field tensor, tensor of rank 2, you write the current density vector. So, this is the field equation which I mentioned, the derivative of the field with respect to the coordinates, to the 4 components, the 4 space time components, right. And let us consider this for mu equal to 0. We are expecting 4 equations. First one is for mu equal to 0. So, let us write it for mu equal to 0, and now the left hand side has nu appearing twice. So, we must sum over nu, alright. So, there are 4 terms, and the right hand side is mu 0 j mu. For mu equal to 0, it is j 0. So, that is your right hand side. So, this is your equation, right, for mu equal to 0. So, let us look at it a little more carefully. Let us get all the components, and you can see that the 0 0 component is anyway 0. So, it does not give you anything, right, and the remaining 3 components will give you the derivative of Ex over c with respect to x, and then Ey over c with respect to y, and Ez over c with respect to z. And on the left hand side you have got mu 0 j 0, but j 0 is c times rho. So, that is the equation that you get, and if you just rearrange this equation now, you have del Ex by del x plus del Ey by del y plus del Ez by del z equal to mu 0 c square rho. But what is mu 0 c square? It is nothing but rho, okay, rho over epsilon 0, it is 1 over epsilon 0, right. So, that is what gives you the first equation. So, this is the same Maxwell's equation, but written in the space time continuum using the tensor notation. Okay. So, you get for mu equal to 0, you recover the Coulomb-Gauss-Maxwell equation, right, and then when you do this for mu equal to 1, let us do it. So, you now have 4 terms again, right, but in each case mu is equal to 1. So, it is the second index which takes different values, and then you take the partial derivatives with respect to x 0, but x 0 is c times t, right. So, take those partial derivatives. Can you do this differentiation in your mind real quick? Pick the terms, what are you getting? Get it ahead of me. So, you get the derivatives of Ex, Bz and minus By with respect to the coordinates. The second one goes to 0. Okay? And if you look at this relation, what is J1? J1 is nothing but Jx. So, you get the x component of the difference of these 2 vectors to be equal to mu 0 J1. And you can see that this is nothing but the x component of the Faraday Lenz law, right. You get the x component of the Faraday Lenz law from this. This is for mu equal to 1. What about mu equal to 2? You get the y component, and then for mu equal to 3 you get the z component, and you recover 2 equations, these 2 equations of Maxwell which are sitting in one tensor single equation, which is the derivative of the field tensor with respect to the space time coordinates, and you see that you have got a very compact representation of Maxwell's equations in this tensor notation. But you need another 2. Where do you get them from, and how would you get them? So, these are obtained from another tensor, which is also an electromagnetic Maxwell field tensor, which is completely equivalent to the previous one, but not the same. Okay? It is similar, but not the same, and you can see how to get it because we wrote the electromagnetic potentials as phi by C and then A. So, our 0th component A0 was phi over C. Now, what is so sacred about having phi over C as A0? You can also have an alternate representation, which I indicate by this blue equation, and the 4 electromagnetic potential is now written with a tilde on top. So, it is A tilde rather than A. So, this is A and this is A tilde, okay? Because we are not going to be using colors everywhere. So, we cannot be distinguished by colors, we need a different notation. So, this is without the tilde and this is with the tilde, and without the tilde you have phi over C as the 0th component, and with the tilde phi over C is the component for mu equal to 3 rather than mu equal to 0. So, these are 2 alternate representations, and you can do exactly the same analysis as we did earlier with this 4 vector. It is completely equivalent, but then you will get an alternative form for all the equations that you got, and the alternative is coming also because the current density vector is now J first and rho C next, rather than the previous case where you had rho C first and J next. So, you have got the red form which is associated with A mu, and you have got the blue form associated with A tilde. So, these are the 2 alternative schemes, and using these 2 alternative schemes you have an alternative electromagnetic field tensor, which I call as G. All right. So, you have got the tilde, which is what I am highlighting here. All right. So, we are now going to work with the tilde, and sure enough this is completely consistent with Maxwell's equations, and this time around we will use the tilde representation of the 4 potential. And if you now take the dual equivalent vector field tensor, so it is now defined in terms of the derivatives of the 4 component potential with respect to the coordinates, but the potentials are now the tilde components, which are the same as the previous one, but ordered differently. So, phi comes not as mu equal to 0, but as mu equal to 3, okay? And then you have got the other 3 components. So, once again you get a tensor of rank 2, you have 16 terms, okay? You have an antisymmetric tensor, so that the off diagonal terms have got opposite sign and the diagonal terms are 0, and using this you have a compact expression for the electromagnetic field tensor, which is similar to what you had in the previous case, but notice that it is also different. Okay? So, when you take the partial derivatives with respect to x, y, z, t and then sum them according to the prescription that we have with us, you are going to get different equations, and sure enough the equation that you now get is del g by del x, you know, with the appropriate superscript indices mu nu and nu, all right. So, with this you get a different set of relations. So, let us see what we get for mu equal to 0. So, for mu equal to 0 you get divergence of B equal to 0. So, this was one of the equations which was missing. We got 2 out of the 4 earlier. Now, we have the divergence of B. So, we have recovered that, and that is contained in this equation del G mu nu over del x nu equal to 0. So, this equation for mu equal to 0, when you sum over nu going from 0, 1 to 3, for 0 you get a term 0, and from the other 3 you get the partial derivatives of bx, by and bz with respect to x, y and z, and that is what gives you the divergence of B when you sum over all the 3, right. So, for mu equal to 1, again you have 4 terms, out of which the second term would give you 0, and the remaining 3 terms are what are shown here, and you see that there is a time derivative of the x component of the magnetic field, but then what it cancels are the x components of the space derivatives of E, which are contained in the expression for the curl of E. So, you can multiply both sides by C, okay, and you essentially get the Faraday-Lenz law for the x component. So, here you have you get the other relations for mu equal to 2 and for mu equal to 3, right, and both the equations that a changing magnetic field can produce an electric field is along with the absence of the magnetic monopole. So, these two laws are contained in one single tensor equation, which has got 4 components. For mu equal to 0, 1, 2, 3. For mu equal to 0, you get the absence of the magnetic monopoles, and for mu equal to 1, 2, 3, you get the 3 components of the vector law for the Faraday-Lenz law. Okay. What about the Maxwell's equations themselves? Are they invariant under Lorentz transformations? So, now if you see this, if you have an arbitrary tensor of rank 2, okay, we now have to see how the field tensor transforms. Okay. So, this is no longer a vector, but it is a tensor. So, electric field and the magnetic field are components of the tensor, which is the larger system of rank 2, rather than separate components of separate vectors of lower rank tensors, which are tensors of rank 1. So, you do not see electric field anymore as 3 components of a tensor of rank 1, but these are 3 elements in the tensor of rank 2. Okay. So, the interpretation of the electromagnetic field has to be along these terms, and if you have any tensor of rank 2 and if you view this tensor from 2 different frames of references, one is the frame S and the other is a barred frame S bar, which is moving with respect to the frame S at a constant velocity, then the same tensor in the new frame will look like T bar rather than as T. And to get T bar from T, you must apply the transformation twice, because now you are having a tensor of rank 2. Okay. So, you must transform it twice, and you can get it by this transformation law that you have got the electromagnetic field tensor in the previous frame, and then you post multiply it by lambda transpose and pre multiply by the matrix lambda. This is how matrix transformations are always carried out, as I am sure you are familiar with, and this field tensor which you will get after this transformation, this is the result which I have written here, and the components are now scrambled. So, E and B get mixed, you end up having admixtures of these, because when you do this, this is a multiplication of 3 4x4 matrices. So, rows and columns, and you know how to do this, and you always do it pictorially in your mind, you go like this and then like this, right? You carry out the multiplication and then add up all the terms. So when you do it, you are going to scramble some of these E and B terms. So that is exactly what happens, and the result that you get is that the components in the frame S bar are E1 bar, E2 bar and E3 bar. The components in the magnetic field will be B1 bar, B2 bar and B3 bar. And how E1 bar, E2 bar, E3 bar are related to E1, E2, E3 and B1, B2, B3 after you carry out this multiplication, and this is a good exercise. It will take you maybe 10 minutes to do it and another 5 minutes to fix the careless mistakes. So a total of 15 minutes is what I would give. You work out this, all right, as homework, and you will find that the components of the electric and magnetic fields transform according to this, and this to me is a real statement of the unity of electric field and magnetic field. In the 3 vector form, you only see that the vector function of one is equal to a function of the other. Del cross E is equal to minus del B by del T. But here you are actually mixing the component of E and B. E2 is mixed with B3. E3 is mixed with B2. Okay? And the coefficients take care of the dimensionality and scaling factors. All right? Now, when you can mix things, then the quantities which are being mixed have to be exactly the same kind of physical entities, right? You do not mix two things just because they have got the same dimensions. That is not the only reason you mix, right? So, torque, for example, what is torque? R cross F, okay? The dimensions are the dimensions of force and displacement, force times length, those are the dimensions. What about the work done? That is F dot D delta L, it has got the same dimensions, but you are not mixing torque with work done. They are different physical quantities. You mix physical quantities, you add or subtract them if and only if they have the same dimensions, which is a necessary property, but not sufficient. They have to be the same kind of things. You mix apples with apples, oranges with oranges. Okay? Both will fall from the tree at the same acceleration due to gravity, right? But you do not mix them, they do not grow on the same trees, they are different. So, here the reason you are able to mix E2 with B3, look at this equation, it is beautiful. This one, E2 minus beta C B3 is equal to E2 bar, and there is of course a gamma there. You are actually adding these two, subtraction is also addition, right? You are actually adding these two, mixing them, superposing them because they are the same physically, and this is a very powerful statement of the unity of electric and magnetic fields. It is far more powerful than the expression of Maxwell's equation in the 3D form. There you do not see that you are actually, you can superpose them in the same way. Okay? So, this is a very powerful statement of the unity of electricity and magnetism, right? And this is the law of transformation that we have referred to. Okay? So, we have applied the boost to the Maxwell field tensor and see how it looks in the second frame of reference, which is moving at a constant velocity with respect to the previous one, and we get these transformation relations and these are the same equations as I had on the previous screen, except that I have organized this screen so that the equations look somewhat larger and they are easier on your eyes, okay. Also on my eyes, because now I can really read the subscripts, okay. It was a little challenging on the previous slide, but here you can see that very easily, that the components of B and E are actually mixed, right. So, these are the transformation. What is an electric field in one frame of reference will look like a mixture of an electric field and a magnetic field in another, okay. It will not be the same. And this is very nicely illustrated in a software which was developed by two of my students, Satish and Venkatesh, when they were undergraduate students, and then their software became obsolete. It was written several years later by Chaitanya Das and Srinivas Murthy, and from the first time when Satish and Venkatesh wrote, it took many years for us to publish this in Resonance. And what this software does is it solves the equation of motion for a charged particle in an electromagnetic field and gets the trajectory. So, that is a simple problem in mechanics, that you have got F equal to dP by dt. F is given by the Lorentz force law, right. You integrate it, put the initial conditions and you get the solution. That is what a trajectory is. But then we ask, how would the trajectory look in a different frame of reference, which is moving at a constant velocity with respect to the previous frame. So, the new frame of reference is also an inertial frame of reference. No pseudo forces will be involved, right. How will the trajectory appear in the other frame of reference? And in the other frame of reference, means you can have the velocity of some particle to be 0 in one frame of reference, it will be non-zero in another, and obviously the V cross B term will be different. So, you will see a different Lorentz force, and then the question is the observer in the different frame going to see different physics? Now, that would be a very serious problem with the laws of physics. So, what he sees is a different set of x0, x1, x2 and x3, okay, which transform according to the Lorentz transformations. But he also sees a different E and B. What is E and B for this is E bar B bar for the second observer, and E bar and B bar involve superpositions of the components of E and B given by this law. And then he can solve an equation of motion in his own frame of reference, integrate it and then get the solution. The other thing you can do is get the solution for the first observer, get x, y, z as a function of t and plot it. That will give you the position vector, the trajectory as its evolution in the configuration space. But you can transform x, y, z, t to x prime, y prime, z prime, t prime and then plot the position vector r prime as a function of t prime and get the solution by carrying out this Lorentz transformation. So, there are two ways of solving this problem. One is by the Lorentz transformation of the trajectory in the first frame, and the second is by setting up a new equation of motion with new E bar and B bar and then solving that second set of equations. Okay? And if physics is the same, then the two trajectories obtained from the transformation, from the Lorentz transformation of the first solution to the solution of the second set of equations of the fields E bar and B bar will have to be completely the same, right. And this is exactly what is done in this work by Satish and Venkatesh. I have that software with me, and here is an example. The details are given in this paper, which I am not referring to, but you can read it up, and it is a very nice software. What it gives is it splits the computer screen into two halves. On the left hand side it gives you the solution that you obtain from the Lorentz transformation of the solution from the first set of equations, and on the right hand side of the screen, you get the solution of the new trajectory that you get by solving a new equation of motion using the transformation of E and B fields. So, essentially you have got the electromagnetic field, it is a relativistic entity, okay. It is a completely relativistic physical quantity described by the special theory of relativity, right. And it brings about how the unity of the electromagnetic field in a very powerful manner. And here is another example. Notice that the solutions trajectories are quite complicated, but they look completely congruent to each other, and you can project the trajectory on the xy plane, which will be the plane of the screen. You can choose that plane to be the yz plane and see if they are congruent on the yz plane also and on the zx, right. So, you can choose this and orient the projections of the trajectories, because you can't see the whole trajectory on a two-dimensional surface, but you can make these choices and convince yourself that the two trajectories are exactly identical, and convince yourself that the point transformation and the field transformation will give you exactly the same solutions. And what is nice is that you can choose what charge particle you want. You can put in an electron with its mass and charge, you can put a proton, you can put some other ion if you like. You can choose the values of the electric and magnetic fields, you can choose them to be along the x axis or the y axis or maybe some other directions, right. And then you can solve this problem in a variety of different ways and convince yourself that the laws of electrodynamics are essentially relativistic and very well described in the tensor notation. In the ordinary vector notation, so vectors are tensors of rank 1, but here I am talking about a tensor of rank 2, which is the electromagnetic field tensor. Then the unity of the electromagnetic field, the invariance of the Maxwell's equations from one frame of reference to another frame of reference, which was at the heart of the special theory of relativity. That Einstein's special theory of relativity was founded by this special consideration that Maxwell's equations are exactly the same in the frame S and the frame S bar. Okay? So, this is a very nice feature. Satish and Venkatesh are now men of positions of importance in the society. Venkatesh is an associate professor at Stony Brook, and Satish has an independent enterprise. Venkatesh wrote to me some time back saying that he had a successful startup company and now he is working on self-driving vehicles. So, they have achieved a lot, but what to me is very interesting is you can see the development of your students. I mean, this is what they did as undergraduate students. They started working on it the first year out of high school, and this lecture is recorded. It will be on the YouTube. I hope that Venkatesh and Satish sometimes watch this and see for themselves that their work is referred to very many years later, what they did as young boys just out of high school. Thank you very much. If there is any question, I will be happy to take. I should of course mention Srinivas Murthy and Chaitanya Das. They did MSc at IIT Madras, and by the time they joined, the software developed by Venkatesh and Satish was no longer working because the platform changed, the graphics cards changed, the machines changed, so the program had to be rewritten. and completely redeveloped, and that was done by Chaitanya Das and Srinivas Murthy. Srinivas wrote to me a few years ago, but I'm not in touch with him for some time. So they did a great job in rewriting it, so it has come out very nicely now. Any question? If not, thank you for now.